What if the universe itself could briefly outshine an entire galaxy with the death of a single star? Welcome. Tonight we explore some of the most extreme events ever discovered in our cosmos. Moments when ordinary astronomy gives way to forces so powerful they reshape entire regions of space in an instant. And what if some of those same catastrophes also create the gold in the jewelry we wear, or the platinum in the devices we use every day? These are not simply destructive. Many leave clues that scientists study for millions of years, revealing how matter behaves when gravity becomes overwhelming or when stars reach the final stages of their lives. Even now, astronomers detect new signals from events that happened billions of years ago. If you enjoy these gentle journeys, like this video, subscribe, or share a thought below. It helps others find their way here, one sleepy soul at a time. But for now, there is nothing you need to do but relax. Let your shoulders soften. Allow your breathing to slow. And as your mind begins to gently unwind, join me as we explore these extraordinary cosmic events together. Let's begin. A supernova can briefly outshine every star in its entire galaxy. For a short time, one dying star can become the brightest object across a system containing billions of suns. The explosion happens when a star reaches a point where its structure can no longer remain stable. In certain supernovae, the core collapses under gravity and the outer layers are blasted outward at tremendous speed. The sudden release of energy can make the star shine billions of times more brightly than it did before. From another galaxy, that single point of light may become visible beside the combined glow of the entire stellar population around it. The brilliance does not last. It rises rapidly, then fades over weeks or months as the expanding debris cools. Yet during that brief interval, astronomers can detect the explosion across enormous cosmic distances. Supernovae have appeared unexpectedly in galaxies that seemed completely ordinary only days earlier. A star that may have gone unnoticed for millions of years can suddenly dominate its galaxy, then disappear forever as a recognizable star. Colliding neutron stars can forge gold heavier than several planet Earths. Gold can be made in an event so violent that two dead stars have to crash together. Neutron stars are the compressed remains of massive stars. When two of them orbit one another, they gradually lose energy until their separation becomes smaller and smaller. Eventually, they collide. The impact throws intensely neutron-rich material into space where atomic nuclei can capture neutrons at extraordinary rates. This process can build some of the heaviest naturally occurring elements in the periodic table. In a single merger, the total quantity of freshly produced heavy elements can be astonishing. Models of observed collisions suggest that the amount of gold alone may reach several times the mass of Earth. Although the exact yield varies from event to event, that material does not remain gathered in one place. It expands into space and eventually mixes with gas that may later form new stars and planets. The golden jewelry on Earth therefore carries a remarkable possibility. Some of its atoms may have been created during a collision between two ancient stellar remnants. Black holes can tear whole stars apart before swallowing their remains. A star does not need to cross a black hole's boundary to be destroyed. If it passes close enough, the difference in gravity between the star's near side and far side can become overwhelming. Those tidal forces stretch the star until its own gravity can no longer hold it together. The result is a tidal disruption event. Instead of falling inward as a complete object, the star is pulled into streams of extremely hot gas. Some of that material escapes on long trajectories. The rest swings back toward the black hole and begins forming a rapidly moving disk. As the gas collides and heats, it can release an enormous burst of radiation that makes a previously inactive galactic center suddenly flare. Astronomers have discovered these events by watching galaxies brighten where no ordinary star could explain the change. The black hole itself remains dark. What becomes visible is the destruction happening around it. By studying the flare, researchers can investigate black holes that might otherwise reveal almost nothing about their presence. Some gamma-ray bursts release more energy than the sun ever will. The most powerful flashes of gamma radiation can release an extraordinary amount of energy within seconds. The sun will shine for roughly 10 billion years during its main lifetime, steadily converting hydrogen into helium and radiating energy into space. A gamma-ray burst can rival or exceed that lifetime output in an astonishingly short interval, especially when astronomers calculate the apparent energy along the narrow direction of its beam. These bursts are not ordinary stellar explosions viewed from farther away. They are highly concentrated events associated with collapsing massive stars or merging compact objects. Much of their radiation can emerge through tightly focused jets moving at speeds extremely close to that of light. If one of those jets points toward Earth, the event appears spectacularly bright, even from billions of light-years away. The burst may be over before a telescope can turn toward it. Automated spacecraft therefore watch the sky continuously and send alerts within moments. What follows can reveal an explosion that briefly became one of the most energetic observable events anywhere in the universe. Neutron stars pack more than a sun inside a city-sized sphere. Take more mass than the sun contains and compress it until the resulting object is only about the size of a large city. That is the scale of a neutron star. These objects form when the core of a massive star collapses after nuclear reactions can no longer support it. Gravity crushes ordinary atomic structure so severely that matter enters a state found nowhere naturally on Earth. The resulting star may measure only around 20 kilometers across, yet it can contain well over 1 solar mass. Its surface gravity is therefore extraordinary. An object dropped nearby would accelerate with a force vastly greater than anything experienced on our planet. The escape speed is also a substantial fraction of the speed of light. Despite this compactness, neutron stars are not black holes. Light can still escape from their surfaces, allowing astronomers to study their heat and rotation. They occupy a remarkable middle ground in nature where familiar matter has been compressed almost as far as possible without disappearing behind an event horizon. Two merging black holes can shake the fabric of spacetime itself. When black holes orbit each other, they do something that cannot be seen with ordinary light. Their motion distorts spacetime and sends ripples outward at the speed of light. These ripples are gravitational waves. At first, the black holes may circle one another slowly. Over time, they radiate energy away through those waves, causing the orbit to shrink. The final moments become extraordinarily rapid. The two objects whirl together faster and faster until their horizons merge and a single larger black hole remains. The changing gravitational field launches a characteristic signal across the universe. By the time that signal reaches Earth, it has stretched and squeezed distances by less than the width of a proton across kilometer-scale detectors. Yet instruments can measure it. The first direct detection announced in 2016 came from two merging black holes more than 1 billion light-years away. Nothing traveled from the collision to shake Earth mechanically. Instead, the geometry of space itself changed by an almost unimaginably tiny amount as the wave passed through. A nearby stellar explosion may have altered life on ancient Earth. Earth has been exposed to exploding stars before, and traces of at least some nearby events appear to remain on our planet. Scientists have discovered deposits of iron-60, a radioactive isotope that is difficult to produce naturally on Earth in significant amounts. It has been found in ancient seafloor material and other geological samples. The best explanation is that debris from supernovae reached the solar system millions of years ago and settled onto Earth. These explosions were not close enough to sterilize the planet, but researchers continue investigating whether they affected the atmosphere or climate. Increased high-energy radiation could potentially change atmospheric chemistry and raise radiation exposure at the surface. Exactly what biological consequences followed remains uncertain, and no dramatic extinction has been conclusively tied to these particular events. What makes the evidence extraordinary is its physical connection to vanished stars. Material created during distant explosions appears to have crossed interstellar space before becoming part of Earth's geological record. Our planet has therefore preserved particles from cosmic catastrophes that occurred in our galactic neighborhood. Magnetars produce magnetic fields trillions of times stronger than Earth's. Magnetars are neutron stars with magnetic fields so intense that everyday comparisons quickly become inadequate. Earth's magnetic field is strong enough to guide compass needles and help shield the planet from charged particles. A magnetar can exceed it by trillions of times. The field near its surface is powerful enough to influence atoms in ways that ordinary terrestrial magnetism never could. Electrons behave differently under such conditions, and the structure of matter itself can be distorted. These fields are thought to arise from extreme conditions during the neutron star's formation, although the precise details remain an active area of research. Magnetars are usually discovered because they produce bursts of X-rays or gamma rays, rather than because their magnetism can be measured directly from nearby. Some rotate only once every few seconds, which is relatively slow for a neutron star. Yet enormous magnetic energy remains stored around them. As that field evolves and stresses the solar crust, sudden rearrangements can release powerful flashes that briefly make a distant magnetar one of the brightest high-energy objects in the sky. Certain stars explode so completely that no remnant survives afterward. Most stellar explosions leave something behind. A collapsed core may become a neutron star, while an even heavier one can form a black hole. But some exceptionally massive stars may end in a different way. Under the right internal conditions, extremely energetic photons begin producing pairs of particles and antiparticles. That change removes pressure that had been helping support the star against gravity. The core contracts, temperatures rise, and oxygen burning can suddenly race out of control. Instead of merely blowing away the outer layers, the thermonuclear explosion can disrupt the entire star. Nothing compact remains. No neutron star survives, and no black hole is immediately formed from a destroyed core. This predicted event is called a pair-instability supernova. Astronomers have searched for possible examples by studying unusually luminous explosions and their chemical signatures. The required stars are thought to be uncommon in the modern universe. They may have been more important much earlier, when stars could form from gas containing far fewer heavy elements than the material available in galaxies today. The universe still carries gravitational echoes from collisions billions of years ago. A violent collision can end long before its gravitational waves finish traveling through the universe. Once created, those waves continue moving outward at the speed of light. They weaken with distance, yet they do not simply vanish when the objects that produce them disappear from view. This means detectors on Earth can register events that happened before our planet even existed in its present form. When a distant pair of black holes merges, the gravitational signal begins crossing intergalactic space while galaxies continue evolving around it. Billions of years later, that distortion may finally pass through Earth. Instruments record only a fraction of a second or a few seconds of the stronger signal. But hidden inside it is information about the original system. Scientists can estimate the masses of the black holes and how rapidly they were moving before merger. In this sense, gravitational wave astronomy does not observe the universe as it is now. It listens to physical disturbances that have been traveling toward us since unimaginably ancient cosmic events. Supernova shockwaves can race through space at millions of miles per hour. The expanding debris from a supernova does not drift gently away from the destroyed star. It can blast outward at thousands of kilometers per second, carrying an immense shock wave into surrounding space. That moving front slams into gas that may have been sitting almost undisturbed for ages. Particles are heated to temperatures high enough to produce X-rays, while magnetic fields become compressed and tangled. Over time, the shock slows as it sweeps up increasing amounts of interstellar material. The remains can still span many light years and stay visible for thousands of years. Famous supernova remnants such as Cassiopeia A allow astronomers to watch this process unfolding long after the original explosion. Different elements glow at different wavelengths, revealing how the stellar interior was thrown outward. The shock is therefore more than the aftermath of a blast. It becomes a moving laboratory where matter is heated, accelerated, and rearranged under conditions impossible to reproduce on the same scale on Earth. A star's death can continue disturbing its neighborhood for generations of human history. One famous supernova remained visible during daylight for several weeks. In the year 1054, observers saw a new light appear in the sky that was bright enough to be noticed during the day. Chinese records describe a guest star near the constellation now called Taurus. It remained visible in daylight for more than 3 weeks and could be seen at night for much longer. At the time, nobody understood that they were witnessing the death of a distant star. Nearly 1,000 years later, astronomers connected those historical observations with the Crab Nebula. The expanding cloud occupies the same region of the sky and contains a rapidly rotating neutron star at its center. Modern measurements of the nebula's motion also point back toward the same era. This makes the event an extraordinary meeting between written history and astrophysics. People living long before telescopes recorded a stellar explosion with their own eyes, and those observations still help scientists study the remnant today. A brief celestial surprise seen by medieval skywatchers became one of the most important supernova remnants in modern astronomy. A collapsing stellar core can rebound in less than 1 second. The center of a massive star can spend millions of years evolving, then undergo catastrophic change almost instantly. Near the end of its life, the core becomes dominated by iron. Fusing iron cannot provide the energy needed to support the star, so gravity finally wins. The core collapses at tremendous speed. Electrons are driven into protons, helping create neutrons while enormous numbers of neutrinos are produced. As the inner region reaches nuclear density, matter suddenly becomes far more resistant to further compression. The collapse halts abruptly and the inner core rebounds. This entire transformation can unfold in well under a second. What happens next is remarkably complicated. A shock wave moves outward, but it can lose energy and stall. Neutrinos streaming from the newly formed compact core may help revive it, allowing the explosion to develop. Researchers still use powerful computer simulations to understand exactly how this works in different stars. A supernova may shine for months, yet the decisive collapse that begins the event can happen faster than a human heartbeat. Some dying stars explode only after stealing matter from a companion. Not every supernova begins with a single massive star collapsing under its own weight. A white dwarf can spend billions of years in relative stability before a nearby companion changes its fate. White dwarfs are dense stellar remnants left behind by stars that were not massive enough to undergo core collapse. In a close binary system, gravity can draw gas from the companion onto the white dwarf. As the remnant gains material, its internal conditions can become increasingly extreme. If carbon fusion ignites explosively through much of the star, a thermonuclear supernova may follow. The white dwarf is torn apart rather than leaving a conventional neutron star behind. These explosions are known as Type Ia supernovae. The exact paths that trigger them are still debated because some may involve two white dwarfs rather than steady feeding from an ordinary companion. What remains remarkable is the delay. A star can appear to have ended its active life long ago, then become the center of a brilliant explosion because another star in the same system alters its future. Astronomers use certain supernovae to measure the universe's accelerating expansion. Some stellar explosions have become tools for measuring distances across billions of light years. Type Ia supernovae are especially valuable because their brightness can be standardized using the way their light rises and fades. If astronomers know how luminous an explosion really was, they can compare that with how faint it appears from Earth and estimate its distance. During the late 20th century, teams studying distant Type Ia supernovae expected to measure how gravity had slowed cosmic expansion. Instead, the explosions appeared dimmer than anticipated for a universe decelerating in the expected way. The evidence pointed towards something astonishing. Cosmic expansion had begun accelerating. This discovery transformed modern cosmology and led to the concept commonly called dark energy, which describes the unknown cause of that acceleration. The supernovae did not explain what dark energy actually is. They revealed its effect. By studying dying stars in distant galaxies, astronomers uncovered a change in the behavior of the universe on the largest possible scale. Stellar destruction became a ruler for cosmic history. The first elements heavier than iron were created during cosmic catastrophes. Ordinary stellar fusion has a natural limit. Stars can build increasingly heavy nuclei in their interiors, but producing elements beyond iron through normal fusion no longer releases useful energy. To create many heavier elements, nature needs environments packed with free neutrons and enormous amounts of energy. Some of those conditions occur during explosive stellar events. Rapid neutron capture allows atomic nuclei to absorb neutrons faster than they can decay, building extremely heavy forms of matter that later transform into stable elements. This mechanism is known as the R process. Modern evidence shows that neutron star mergers are major sites for it, while certain rare stellar explosions may also contribute. The exact history of where different heavy elements originated remains an active field of research. What is clear is that much of the periodic table could not have been assembled through calm stellar burning alone. Some atoms required cosmic emergencies. Material later incorporated into planets was enriched by catastrophic events that occurred before the solar system formed. The chemistry of ordinary matter, therefore, carries a record of ancient violence. Supernova remnants can continue expanding for tens of thousands of years. A supernova may be brief, but its physical footprint can survive through vast stretches of time. After the initial explosion, stellar debris expands into surrounding interstellar gas and gradually forms a supernova remnant. During its early stages, the ejecta move outward rapidly and begin sweeping up material. Eventually, the amount of captured gas becomes greater than the original mass thrown from the star. The remnant then enters a slower phase in which its shock continues expanding while losing energy. Over tens of thousands of years, the structure can spread across dozens of light years. Its appearance also changes dramatically. Young remnants may glow strongly in X-rays because their gas is extremely hot. Older remnants can become large optical shells traced by filaments of cooler material. Eventually, the boundary becomes difficult to distinguish from the interstellar medium around it. By then, the exploded star has effectively mixed part of itself into the galaxy. Long after the flash has vanished, its expanding remains continue transporting matter and energy through the space between other stars. The Crab Nebula surrounds a star that exploded nearly a millennium ago. At the center of the Crab Nebula sits a tiny remnant whose behavior is almost as remarkable as the explosion that created it. The Crab Pulsar is a neutron star rotating around 30 times every second. Each turn sweeps beams of radiation through space, producing pulses detected across several wavelengths. Those pulses are so regular that astronomers can monitor tiny changes in the star's rotation with remarkable precision. Around it lies a glowing nebula several light years across. The pulsar continuously releases a wind of energetic particles that crashes into the surrounding material and helps power the nebula's distinctive radiation. Detailed images reveal structures that change over surprisingly short timescales, including moving wisps near the central star. The system therefore allows astronomers to study both the aftermath of the ancient supernova and the continuing activity of the object left behind. The explosion happened in historical times, but its engine is still running. Nearly 1,000 years later, the collapsed core continues injecting energy into the debris that once belonged to its parent star. Ancient observers recorded stellar explosions long before telescopes existed. Some of the earliest useful supernova observations were made with nothing more than careful human eyesight. Astronomers in several historical cultures watched the sky closely enough to notice when a bright new point suddenly appeared where no star had been recorded before. Chinese court astronomers were particularly systematic. Their records of guest stars sometimes included where the object appeared, how bright it looked, and how long it remained visible. These descriptions can now be compared with known supernova remnants. In several cases, the connection is convincing enough to give modern researchers an approximate explosion date. That historical information matters because the age of a remnant helps scientists calculate how quickly its debris has expanded and how its brightness has changed. Written observations made for entirely different reasons have therefore become scientific data centuries later. They also reveal something deeply human about astronomy. Long before anyone understood stellar evolution, people recognized that the supposedly unchanging heavens could produce sudden new lights. Their records preserved events whose physical remains are still being studied with modern observatories. Some supernovae shine unusually brightly because magnetars power them from within. A supernova can receive a second source of energy after the initial explosion has already begun. In some extraordinarily luminous events, astronomers suspect that the newly formed neutron star is a rapidly spinning magnetar. At birth, such an object can rotate far faster than most magnetars observed later in life. It also contains an immense reservoir of rotational energy. As its powerful magnetic field slows the spin, some of that stored energy can be transferred into the expanding supernova debris. The surrounding material absorbs the added power and radiates it outward, keeping the explosion brighter than radioactive decay alone would normally allow. This idea helps explain a class known as superluminous supernovae, which can greatly exceed the brightness of more familiar stellar explosions. Scientists test the model by comparing observed light curves with predictions for spinning magnetars. Other mechanisms may contribute in some cases, so the picture is still developing. Yet the possibility is remarkable. The compact object born inside an explosion may immediately begin powering the very debris created during its own formation. Pair-instability supernovae may destroy stars hundreds of times heavier than the Sun. Some of the largest stars ever formed may die without leaving any central remnant at all. Deep inside an exceptionally massive star, temperatures can become so extreme that energetic photons begin turning into pairs of particles. This removes radiation pressure from the core at exactly the wrong moment. Gravity suddenly gains the advantage, forcing the interior to contract and heat even further. Oxygen then begins burning at a runaway rate. Instead of producing a normal collapse, the resulting thermonuclear reaction can release enough energy to reverse the contraction and blow the entire star apart. Astronomers call this a pair-instability supernova. The process is expected only within a particular range of stellar masses, especially in stars containing relatively few heavy elements. Such giants may have been more common in the early universe. Their explosions would have scattered enormous quantities of newly formed elements into surrounding space. Finding a convincing example today would give astronomers a rare chance to witness a stellar death so complete that the original star is physically erased. Failed supernovae may vanish quietly as their stars collapse into black holes. A massive star does not always announce its death with a brilliant explosion. In some cases, the core may collapse so powerfully that the outward blast never succeeds. The star begins the same catastrophic process that can create a supernova, but the shock loses its struggle against gravity. Material continues falling inward until a black hole forms. If most of the star follows, the expected explosion may never appear. Astronomers have searched for these failed supernovae by repeatedly photographing large numbers of massive stars in nearby galaxies. The strategy is wonderfully simple. Find a luminous star, keep watching it, and ask whether it eventually disappears without producing the expected final flash. Several intriguing candidates have been identified. One red supergiant appeared to brighten modestly before fading dramatically from view. Dust can complicate such observations, so proving a direct collapse is difficult. If these silent deaths are common, they could explain why astronomers observe fewer ordinary supernovae from the most massive stars than simple stellar evolution models once predicted. A supernova can compress surrounding gas and trigger entirely new stars. The death of one star can help create the next generation. When a supernova shock wave sweeps through a nearby molecular cloud, it suddenly places cold interstellar gas under intense pressure. Regions that were previously too diffuse to collapse may become squeezed until gravity begins pulling them together. Dense pockets can then fragment into smaller clumps, eventually forming protostars. The process does not happen after every supernova because the timing and distance have to be favorable. A shock that is too strong may simply tear a cloud apart, while one that is weakened too much may barely disturb it. Yet observations of expanding bubbles and star-forming regions suggest that triggered starbirth can occur around energetic stellar feedback. The newborn stars may even contain material expelled by the original explosion. This creates a remarkable cycle. One generation of stars ends by violently rearranging the gas around it, and that disturbance can help assemble another generation. Stellar death is therefore not simply an ending. Under the right conditions, it can become part of the machinery that begins new suns. Shocked atoms inside supernova remnants can glow brightly in invisible X-rays. Much of a supernova remnant's most dramatic light cannot be seen by human eyes. When the expanding blast wave strikes surrounding gas, particles are heated to temperatures of millions of degrees. At those temperatures, atoms lose many of their electrons and become highly ionized. As electrons move between energy states or collide with other particles, the hot plasma produces X-rays. Space telescopes can separate this radiation into different energies and reveal which elements are present. Oxygen may dominate one region while silicon or iron appears elsewhere. These maps allow astronomers to reconstruct how the destroyed star was layered before it exploded. They can even trace knots of material that were launched in different directions. X-ray images of remnants such as Cassiopeia look completely different from ordinary visible light photographs because they reveal the hottest components of the wreckage. The colors used in published images are usually assigned to different energy bands rather than showing what an eye would see. They transform invisible radiation into a detailed map of a stellar interior that no longer exists. Radioactive elements keep many supernovae shining long after the initial explosion. The first flash of a supernova is not the only reason it remains bright. Inside many explosions, enormous temperatures create unstable radioactive isotopes. One especially important example is nickel-56. It decays into cobalt-56, which later decays into stable iron-56. Each step releases energy in the form of particles and high-energy radiation. The expanding debris absorbs much of that energy and converts it into visible light. This radioactive heating can sustain the glow for weeks or months after the original shock has passed through the star. Astronomers study how the brightness declines because the pattern reveals which isotopes are powering the fading remnant. The amount of nickel produced also tells them about conditions during the explosion itself. In some supernovae, radioactive decay dominates the later light curve so clearly that the physics of unstable nuclei becomes visible across another galaxy. A handful of atoms changing their internal structure would seem insignificant. Multiplied across a vast cloud of stellar debris, the same process can illuminate space long after the star's violent destruction has ended. Neutrinos escape collapsing stars before visible light reaches the surface. When the core of a massive star collapses, one of the earliest warnings can arrive in particles that pass almost effortlessly through matter. Neutrinos interact so weakly that trillions move through your body every second without leaving any noticeable trace. During stellar collapse, however, they are produced in astonishing numbers. The newly forming compact core releases a huge burst of them as matter is compressed and nuclear reactions change protons and electrons. Because neutrinos can pass through the overlying star much more readily than photons, they escape before the visible explosion reaches the surface. Light still has to wait for the shock wave to travel outward through the star's layers. For a nearby supernova, neutrino detectors on Earth could therefore register the event before telescopes see the star brighten. Automated alert systems already exist to take advantage of this possibility. A sudden burst could give astronomers valuable time to turn instruments toward the correct region of sky. The universe may effectively whisper that a star has collapsed before the heavens visibly announce it. Scientists detected neutrinos from a supernova outside the Milky Way. In February of 1987, detectors deep underground recorded something extraordinary. A small burst of neutrinos arrived from the direction of the Large Magellanic Cloud. Hours later, astronomers were watching a supernova there that became known as SN 1987A. Only about 24 neutrinos were detected across several experiments. Yet those few particles transformed astrophysics. They had traveled roughly 160,000 years through space before reaching Earth. Their arrival confirmed a central prediction about core collapse supernovae. Most of the gravitational energy released during the collapse emerges as neutrinos rather than visible light. The observation also allowed researchers to test how these elusive particles behave across an enormous distance. It remains the only supernova from which neutrinos have been directly detected so far. Modern detectors are much larger and more sensitive, so another sufficiently nearby stellar explosion could produce thousands of signals. The next burst would let scientists examine the hidden core of a collapsing star in detail that optical telescopes alone could never provide. Some stellar explosions leave rapidly spinning neutron stars called pulsars. After certain massive stars explode, their crushed cores can become cosmic beacons. A pulsar is a rotating neutron star whose magnetic axis is usually tilted away from its spin axis. Charged particles accelerate around the magnetic poles and produce beams of radiation. As the star turns, those beams sweep through space. If one crosses Earth, telescopes detect a pulse each time the star completes a rotation. The effect resembles a lighthouse, although nothing is literally switching on and off at the source. The beam is simply moving past us. Pulsars were discovered in the late 1960s when radio astronomers noticed signals repeating with astonishing regularity. The first source was so unexpected that researchers briefly considered whether an artificial transmission might be responsible. Nature soon provided the answer when more examples appeared. Today, thousands are known. Their timing is so precise that astronomers can use them to investigate gravity, map interstellar plasma, and study unseen companions. A star can therefore die explosively and leave behind something that behaves like one of the universe's most accurate natural clocks. Pulsars can sweep radio beams across Earth with clock-like precision. Some pulsars are so regular that the arrival times of their signals can be predicted with remarkable accuracy. Each radio pulse may look simple, but it comes from an object rotating in a stable rhythm across enormous spans of time. Astronomers measure when individual pulses reach Earth and compare them with a mathematical timing model. Tiny departures can reveal extraordinary things. A pulsar may be orbiting another star, moving through curved spacetime, or experiencing subtle changes in its own rotation. Even planets have been discovered around pulsars because their gravity shifts the neutron star back and forth enough to alter the timing. The first confirmed planets outside our solar system were found this way. Interstellar gas also affects the pulsars because different radio frequencies travel through ionized material at slightly different speeds. Correcting for that delay gives information about matter between the stars. A seemingly repetitive signal therefore becomes a precision experiment stretching across light years. Every pulse carries not only the rhythm of the neutron star but also evidence about whatever has influenced its journey toward Earth. The fastest known pulsars complete hundreds of rotations every second. A neutron star can spin so quickly that its surface travels through space at a significant fraction of light speed. The fastest confirmed pulsars rotate more than 700 times each second. These objects are called millisecond pulsars because a complete turn takes only a few thousandths of a second. They were not necessarily born spinning this rapidly. Many appear to have been accelerated later by stealing gas from a companion star. As matter spirals inward, it transfers angular momentum to the neutron star and gradually spins it up. This recycling process can transform an older pulsar into an exceptionally stable rapid rotator. There is a physical limit to how fast such a star can turn. If rotation became extreme enough, material at the equator would no longer remain gravitationally bound. Measuring the fastest pulsars therefore helps scientists investigate the strength and internal structure of neutron stars. Their rotation pushes matter toward conditions that laboratories cannot approach. Something heavier than the Sun can whirl hundreds of times per second without tearing itself apart. Neutron star crusts may be the strongest known material in nature. The outer solid layer of a neutron star is unlike any crust found on a planet. Gravity compresses atomic nuclei into structures packed at extraordinary density, while electrons move through the material under immense pressure. Computer simulations suggest that this nuclear crust may be around 10 billion times stronger than steel when compared by breaking strain. That does not mean a piece could simply be brought to Earth and used as construction material. Neutron star matter exists only because crushing gravity maintains those conditions. Remove it from that environment and it would change catastrophically. The strength matters because a rotating neutron star can support tiny distortions rather than becoming perfectly spherical. Those distortions may generate continuous gravitational waves if the star spins rapidly enough. The crust can also store stress produced by changes in rotation or magnetic fields. Eventually, it may fail suddenly. Understanding how it breaks helps researchers interpret abrupt behavior seen in neutron stars. The strongest known material in the universe may therefore reveal itself not through something we can touch, but through distant stars trembling under their own impossible weight. Mountains on neutron stars may rise only millimeters above their surfaces. On Earth, gravity allows mountains to tower kilometers above sea level. On a neutron star, gravity is so overwhelming that even the strongest crust can support only tiny irregularities. What astronomers casually call a mountain might rise mere millimeters or centimeters above the average surface depending on the star and the crust strength. That sounds almost perfectly smooth, but the distortion can still matter. A neutron star contains more than a solar mass, so even a microscopic departure from perfect symmetry involves an enormous amount of matter. If the star rotates rapidly, such a bump could make its gravitational field vary slightly with every turn. In principle, that creates a continuous stream of gravitational waves. Detectors are searching for these faint signals from known pulsars. A successful detection would reveal information about the star's interior and show how much strain its crust can actually endure. The scale is wonderfully counterintuitive. A feature too small to step over on Earth could become astrophysically significant when attached to one of the densest objects in existence. A teaspoon of neutron star matter would weigh billions of tons. The enormous density of neutron stars comes from what happens when atoms are crushed beyond their familiar form. In ordinary matter, most of an atom's volume is effectively empty space between its tiny nucleus and surrounding electrons. During stellar collapse, pressure becomes so intense that electrons are forced much closer to nuclei. Many combine with protons through nuclear reactions that produce neutrons. The resulting material is packed at densities similar to those inside atomic nuclei. A teaspoonful is often estimated to have a mass of billions of tons. Such a sample could never simply sit on a kitchen table. Outside the neutron star's crushing gravity, the material would not remain in the same state. The comparison is useful because it shows how dramatically stellar collapse changes matter. A neutron star achieves this density across an object many kilometers wide. Its tremendous mass is not hidden inside a tiny central point. The entire interior is compressed into exotic phases that physicists are still trying to understand. Familiar atoms have effectively been pushed to the limit of what ordinary matter can endure. Pulsar glitches occur when neutron stars suddenly spin slightly faster. Pulsars usually slow down very gradually as they lose rotational energy. Every so often, however, some of them do the opposite. Their spin rate suddenly jumps upward by a tiny amount. Astronomers call this a glitch. The change may be minuscule, yet precision timing makes it unmistakable. One leading explanation involves superfluid material inside the neutron star. This fluid can rotate through microscopic vortices that behave differently from the solid crust surrounding them. As the outer star slows, some internal vortices may remain temporarily pinned in place. A growing difference develops between the rotation of the crust and the hidden fluid beneath it. Eventually, large numbers of vortices can shift suddenly and transfer angular momentum outward. The crust responds by spinning faster. Afterward, the pulsar gradually adjusts toward its previous trend. Glitches provide one of the rare ways to probe processes deep inside neutron stars. Scientists cannot see those interiors directly, but a tiny change in timing can reveal that enormous reservoirs of quantum fluid are moving beneath the surface of a distant collapsed star. Starquakes can crack magnetar crusts and unleash enormous bursts of radiation. A magnetar's magnetic field does not remain perfectly static. As it changes, it can twist and strain the solid crust beneath the surface. The crust may resist for years before suddenly shifting or fracturing. That abrupt rearrangement is often described as a starquake. Unlike an earthquake, the disturbance occurs on an object whose gravity and magnetic field dwarf anything found on our planet. The quake can alter magnetic structures outside the star and accelerate enormous numbers of particles. Energy then erupts as X-rays or gamma rays. Some bursts last only fractions of a second, while rarer giant flares release vastly more power. Astronomers infer the connection between crustal stress and magnetic activity by studying how bursts cluster and how Magnetars' rotation changes during active periods. The details remain complex because events inside the star and changes in its external magnetic field can influence each other. What begins as stress in a rigid crust only kilometers across can become a flash visible from across the galaxy. A microscopic fracture can have astronomical consequences. A powerful magnetar flare once disturbed Earth's upper atmosphere. On December 27, 2004, an enormous pulse of gamma rays swept across the solar system. It came from a magnetar known as SGR 1806-20, located tens of thousands of light-years away. The first fraction of a second was so intense that several spacecraft detectors were overwhelmed. Even at that extraordinary distance, the radiation reached Earth strongly enough to affect the ionosphere. This upper region of the atmosphere contains charged particles and normally responds most noticeably to solar activity. For a distant neutron star to alter it demonstrates the astonishing power of the flare. The event was followed by a fading signal whose changing brightness reflected the rotation of the magnetar. Researchers concluded that an enormous rearrangement of magnetic energy had taken place. Had the same flare occurred much closer, its effects would have been far more severe. Instead, Earth received a harmless but measurable disturbance from the other side of the Milky Way. A star only kilometers wide briefly reached across a substantial fraction of our galaxy and touched the atmosphere above us. Magnetars may be born when exceptionally fast stellar cores collapse. Why some neutron stars become magnetars, while others do not, remains one of their central mysteries. One influential idea begins during the final moments of the parent star. If the collapsing stellar core is rotating extremely quickly, violent motions in the newly formed neutron star may amplify magnetic fields through a dynamo process. Similar principles operate in other astrophysical objects, but the conditions here are vastly more intense. Convection, rotation, and electrically conducting matter could work together to build a magnetic field of extraordinary strength within seconds. Other theories suggest that some parent stars already possess unusually strong magnetic fields that become greatly intensified during collapse. Observations provide clues, but no single explanation has settled the question. Astronomers compare magnetars with ordinary pulsars and study the star clusters where some of them were born. They also examine supernova remnants for evidence about the original explosion. The answer matters because magnetars represent a rare path through stellar evolution. Two massive stars may begin with broadly similar ingredients. Yet one leaves an ordinary neutron star while another creates the most magnetic object known. Neutron stars can cool from billions of degrees surprisingly quickly. A newborn neutron star begins life unimaginably hot. Immediately after collapse, its interior can reach temperatures of tens or hundreds of billions of degrees. Yet it sheds heat far more efficiently than an ordinary glowing object. During the earlier stages, much of the cooling occurs through neutrinos produced deep inside the star. These particles escape with energy that would otherwise remain trapped as heat. Over thousands of years, the surface temperature falls dramatically. Although the star can still remain hot enough to shine strongly in X-rays, the exact cooling rate depends on what matter exists in the interior. Certain nuclear reactions may produce neutrinos very efficiently, while superfluid phases can change how heat moves and how particles interact. Astronomers therefore compare the measured temperatures of neutron stars with estimates of their ages. A star cooling faster or slower than expected can reveal hidden physics occurring kilometers beneath an inaccessible surface. Temperature becomes a diagnostic tool. Watching a dead star lose its heat can tell researchers what forms of matter may exist at densities no experiment on Earth can reproduce. Superfluid matter may flow without friction inside neutron star interiors. Deep inside a neutron star, matter can enter a quantum state with no everyday equivalent at human scale. Under enormous pressure and at sufficiently low temperatures, neutrons are expected to pair up and form a superfluid. A superfluid can move without the ordinary viscosity that slows normal liquids. Similar behavior has been created in laboratory systems at extremely low temperatures, but neutron stars provide a natural version involving nuclear matter under crushing density. The superfluid does not simply swirl like water inside a container. Its rotation is organized into quantized vortices. Each vortex carries a fixed amount of circulation and vast numbers of them thread through the interior of a spinning star. Their interactions with the crust and other components may influence sudden changes in pulsar rotation. Superfluidity also affects heat capacity and neutrino emission, so it can change how neutron stars cool. Astronomers have even interpreted temperature changes in some young neutron stars as possible evidence that superfluid transitions are occurring. Quantum mechanics may therefore control the behavior of matter across an entire stellar remnant. Nuclear pasta may form bizarre structures beneath neutron star crusts. Just before the solid crust gives way to the deeper interior of a neutron star, matter may organize itself into shapes that physicists jokingly named after food. At these densities, two powerful influences compete. Nuclear forces try to bind protons and neutrons together, while electrical repulsion pushes positively charged regions apart. The compromise may produce sheets, rods, and tangled structures rather than neat spherical nuclei. Researchers use names such as lasagna and spaghetti because the simulated shapes resemble familiar pasta. The humor hides serious physics. Nuclear pasta could be among the strongest material configurations in the universe. It may influence how heat travels through the crust and how the star's magnetic field evolves. Its structure could also affect neutrino interactions and the behavior of matter during neutron star mergers. No scientist can collect a sample, so the evidence comes from theoretical calculations and sophisticated simulations. A region only a short distance beneath a neutron star surface may contain matter arranged into forms that do not naturally exist anywhere on Earth. Some neutron stars hide beneath thick atmospheres of carbon or hydrogen. A neutron star may have a solid surface, but that surface is not necessarily exposed directly to space. Gravity can hold a remarkably thin yet optically important atmosphere above it. Because heavier elements tend to sink rapidly, the uppermost layer can become dominated by the lightest material available. Hydrogen and helium are common possibilities, while some young neutron stars appear consistent with carbon atmospheres. The choice matters enormously when astronomers interpret the light. Different atmospheric elements shape the outgoing spectrum in different ways, changing estimates of the star's temperature and apparent size. A blackbody model can therefore give misleading results if the atmosphere is ignored. Researchers compare X-ray observations with detailed models of how radiation passes through intensely magnetized plasma. In some cases, identifying the atmospheric composition helps constrain the radius of the neutron star itself. That radius is one of the keys to understanding ultradense matter. Something as seemingly delicate as a layer of gas above a collapsed star can therefore influence our best attempts to determine what lies deep inside it. Binary pulsars provided early indirect evidence that gravitational waves exist. Long before instruments directly measured gravitational waves, astronomers found compelling evidence through a pair of orbiting neutron stars. In the 1970s, Russell Hulse and Joseph Taylor discovered a pulsar locked in a tight binary system. Because the pulsar emitted precisely timed radio signals, researchers could track its orbit with exceptional accuracy. General relativity predicted that such a system should lose energy by radiating gravitational waves. If that happened, the two stars would slowly spiral closer together and complete each orbit slightly faster. Years of observations showed exactly that behavior. The orbital period decreased at the rate predicted by Einstein's theory with remarkable precision. No gravitational wave detector had yet felt the waves themselves, but the stars were clearly losing the correct amount of energy. The discovery earned Hulse and Taylor the Nobel Prize in Physics. It was a beautiful example of astronomy testing fundamental physics through natural objects. Two collapsed stars became a cosmic laboratory, revealing an invisible form of radiation decades before humanity developed technology sensitive enough to detect it directly. Merging neutron stars can produce brief bursts of gamma-ray light. For years, astronomers suspected that short gamma-ray bursts came from compact objects colliding. The idea became dramatically stronger when gravitational waves from a neutron star merger were detected in 2017. Less than 2 seconds after the gravitational signal, satellites recorded a short burst of gamma rays from the same general region of sky. Telescopes then found a rapidly changing optical source in a nearby galaxy. For the first time, different kinds of cosmic messenger had traced the same event. The gamma rays are thought to arise from an ultrafast jet launched after the merger, although exactly how that jet forms depends on the object left behind and the surrounding debris. Because the beam is narrow, many mergers will not point directly toward Earth and may appear very different. That explains why gravitational wave observations are so valuable. They can reveal collisions that gamma-ray telescopes might miss. A flash lasting only a couple of seconds can therefore mark the instant when two neutron stars finish an orbital dance that may have lasted billions of years. The first observed neutron-star merger transformed gravitational wave astronomy. On August 17, 2017, gravitational wave observatories detected a signal unlike the earlier black hole mergers. It lasted much longer and matched two neutron stars spiraling together. Astronomers rapidly shared the location estimate with observatories around the world. Within hours, telescopes found a new source of light in the galaxy NGC 4993. Over the following days, nearly every major branch of astronomy joined the investigation. Radio telescopes, optical instruments, and X-ray observatories tracked different parts of the aftermath. The event became known as GW 170817. It marked the beginning of truly multi-messenger gravitational wave astronomy because information arrived through both spacetime vibrations and electromagnetic radiation. Researchers used the observations to test the speed of gravity, study heavy element production, and investigate the behavior of ultradense matter. The event also provided an independent way to estimate cosmic distances. One collision suddenly connected fields that had often worked separately. It demonstrated that gravitational waves were not merely new signals to detect. They were a new way to coordinate our view of the universe. Kilonova explosions reveal newly forged heavy elements through changing colors. After two neutron stars collide, radioactive debris thrown into space can create a transient glow called a kilonova. It is much fainter than a typical supernova, yet its rapidly changing color carries remarkable information. Freshly created heavy nuclei are unstable and begin decaying almost immediately. That radioactive decay heats the expanding material and powers the light we observe. At first, some kilonovae can appear relatively blue. As the debris expands and its composition becomes more influential, the emission may shift toward red and infrared wavelengths. Elements known as lanthanides are especially important because their complex atomic structures make the ejecta highly opaque to visible light. By tracking this color evolution, astronomers can estimate what kinds of nuclei were produced and how much material escaped. The kilonova observed after the neutron star merger in 2017 gave powerful support to this picture. Its changing light allowed researchers to watch nuclear physics unfold across another galaxy. Colors lasting only days revealed an element-making process that had been predicted for decades. Platinum may be created alongside gold during neutron star collisions. Gold attracts attention, but it is only one member of a much larger family of heavy elements that can emerge from neutron-rich cosmic debris. Platinum is another. During a neutron star merger, nuclei can absorb neutrons in rapid succession before radioactive decay has time to pull them back towards stability. This process allows matter to climb into regions of the nuclear chart that ordinary stellar fusion cannot easily reach. As unstable nuclei later decay, they populate a range of stable heavy elements that includes platinum group metals. The exact proportions depend on the density, temperature, and neutron richness of the ejected material. Different parts of the merger can therefore manufacture different mixtures. Scientists compare theoretical predictions with kilonova observations and with the abundance patterns measured in ancient stars. Those old stars preserve chemical evidence from earlier generations of cosmic events. Platinum on Earth was incorporated into the material that formed the solar system long after its atoms were made. A metal prized for resisting corrosion may owe its existence to matter that was once violently expelled from colliding stellar corpses. Neutron star mergers can leave either magnetars or black holes behind. The collision is not necessarily the final chapter of a neutron star merger. What remains at the center depends strongly on the combined mass and on the properties of ultradense matter. If the merged object is too heavy for any neutron star to support, it can collapse almost immediately into a black hole. In other cases, rapid rotation may temporarily help resist gravity. The remnant can survive for milliseconds, seconds, or perhaps much longer before eventually collapsing. If its mass remains below the relevant stability limit, it could persist as an extremely massive neutron star with an intense magnetic field. Such an object may behave like a newborn magnetar. These different outcomes matter because they change the surrounding explosion. A long-lived central remnant can inject additional energy into the expanding debris, while rapid black hole formation may produce a different pattern of radiation. Astronomers try to infer the outcome from gravitational waves, gamma rays, and later emission. Each merger therefore becomes a test of the maximum mass that neutron star matter can withstand before gravity wins completely. Dense stellar collisions can launch jets moving almost as fast as light. Some of the most spectacular structures created by compact object mergers are narrow jets of matter moving at relativistic speeds. To launch one, material falling toward the central remnant forms a hot rotating disk. Powerful magnetic fields can thread the disk and the object at its center. Under favorable conditions, energy is channeled along the rotation axis and drives a tightly focused outflow. The particles in the jet can move so close to light speed that relativistic effects dominate what observers see. Radiation becomes strongly concentrated in the forward direction, and time intervals measured by distant telescopes can appear compressed. The jet must also force its way through debris expelled during the collision. If it succeeds, it can produce high-energy emission and later create a widening afterglow as it slams into surrounding gas. The structure is not always a simple uniform beam. Observation suggests some jets possess energetic cores surrounded by slower material. By watching the afterglow brighten and fade, astronomers can reconstruct the geometry of an explosion that occurred far beyond direct resolution. Relativistic jets appear brighter when they point almost directly toward Earth. Orientation can completely change how an extreme cosmic event looks. When material in a jet moves close to light speed, relativity concentrates much of its radiation in the direction of travel. An observer positioned near the jet axis therefore sees a source that appears far brighter than someone viewing the same event from the side. This effect is called relativistic beaming. It helps explain why some active galaxies look extraordinarily luminous and why gamma-ray bursts can be visible from immense distances. The underlying source does not radiate equally in every direction. Geometry determines whether Earth lies inside the narrow cone of enhanced emission. Motion also changes the observed timing. Variations can appear faster because photons emitted later along the approaching jet have less additional distance to travel toward us. The opposite jet may look much fainter because its radiation is beamed away. Astronomers must account for these effects before estimating the true power of the source. Sometimes the difference between an apparently overwhelming cosmic beacon and a modest distant object is simply which direction its jet happens to face. Gamma-ray bursts are visible across most of the observable universe. A gamma-ray burst can be detected from distances so great that its light began traveling when the universe was still young. These events are valuable precisely because their brief brilliance can cut through cosmic distance. High-energy satellites first locate the burst, then ground-based telescopes race to observe its fading afterglow. If astronomers obtain a spectrum, they can measure how strongly cosmic expansion has stretched the light toward longer wavelengths. Some bursts have been confirmed at redshifts corresponding to more than 13 billion years of light travel time. That makes them potential probes of the era when the first generations of stars and galaxies were forming. Unlike galaxies, which may be faint and difficult to study individually at such distances, a burst can temporarily advertise the presence of a single dying star with extraordinary intensity. The event itself soon disappears, but its afterglow may illuminate gas along the line of sight. Gamma-ray bursts therefore provide brief beacons from epochs that ordinary telescopes struggle to examine. A stellar death can become visible across nearly the entire observable cosmos. Long gamma-ray bursts often accompany the deaths of massive stars. The connection between long gamma-ray bursts and stellar death became clear when astronomers found supernovae emerging beneath some fading afterglows. These bursts generally last longer than about 2 seconds, though duration alone does not tell the whole story. The leading model involves a massive star whose core collapses and forms a compact central object. Instead of producing only a roughly spherical explosion, the system launches narrow relativistic jets through the star. If one jet successfully punches through the outer layers and points toward Earth, we detect a powerful burst of gamma rays. The surrounding star can still explode as a broad-lined Type IC supernova after losing its outer hydrogen and helium. Not every such supernova makes a detectable burst because the jet may fail or point elsewhere. The association gives astronomers a direct link between high-energy transients and the final evolution of certain massive stars. A gamma-ray burst is therefore not simply an unusually bright supernova. It is evidence that the collapse created an organized engine capable of driving matter outward at nearly light speed. Short gamma-ray bursts usually arise from merging compact stellar remnants. For decades, short gamma-ray bursts were harder to explain than their longer relatives. They flashed for less than about 2 seconds and often occurred far from obvious regions of active star formation. That distribution suggested older stellar systems rather than recently formed massive stars. The strongest explanation became the merger of compact remnants, especially 2 neutron stars. Such binaries can survive for millions or billions of years while their orbits slowly shrink. By the time they collide, they may have traveled far from the places where their original stars were born. Gravitational wave observations eventually provided decisive support for this picture. Some short bursts may also arise when a neutron star merges with a black hole. The details of jet formation are still being studied, and not every compact merger will produce a detectable burst. What makes the phenomenon remarkable is the timescale contrast. A binary can evolve almost invisibly for longer than complex life has existed on Earth, then release its most obvious signal in less time than it takes to speak a sentence. A gamma-ray burst beam could miss Earth despite enormous nearby energy. The most important thing about many gamma-ray bursts is not simply how powerful they are, but where their energy goes. Much of the radiation is concentrated into narrow jets rather than emitted equally in every direction. That means a burst could occur comparatively nearby and still look unimpressive from Earth if neither jet points toward us. Astronomers might instead notice a supernova, a kilonova, or a faint afterglow produced as the outflow slows and spreads. This geometry creates a major observational bias. The bursts we detect most easily are the ones whose beams happen to sweep across our planet. For every event aimed toward Earth, many others may be pointed elsewhere. Researchers try to estimate this hidden population by studying jet opening angles and searching for explosions whose later emission becomes visible after the beam widens. The true rate of these events is therefore higher than the number of detected gamma-ray flashes suggests. Cosmic violence can occur surprisingly close by without producing its most dramatic signature in our sky simply because the universe aimed the beam in another direction. Some gamma-ray bursts last less than the blink of an eye. The shortest high-energy flashes can begin and end before a person could consciously react to them. Satellites have recorded gamma-ray bursts lasting only fractions of a second, which forces astronomers to infer an astonishing amount of physics from a tiny interval of data. Such brevity tells researchers that the region producing the initial radiation must itself be extremely compact. A source cannot coordinate a rapid brightness change across an area larger than light could cross during that change. Millisecond structure therefore points toward engines on the scale of compact stellar remnants rather than ordinary stars. Within the burst, individual spikes may appear even faster, suggesting turbulent or magnetic processes inside an outflow traveling almost at light speed. Instruments designed to study these events must monitor the sky continuously because there is no opportunity to receive advanced warning and aim a telescope. By the time an alert reaches human observers, the primary flash is already history. The shortest bursts demonstrate how the universe can release information about an enormous catastrophe in a signal briefer than an involuntary blink. Others continue radiating high-energy light for several hours. Not every gamma-ray burst fits neatly into the familiar picture of a brief flash followed by a fading afterglow. Astronomers have discovered ultra-long events whose high-energy activity continues for thousands of seconds, and sometimes much longer. Their unusual duration suggests that the central engine can remain active instead of shutting down quickly. Several explanations have been proposed. One possibility involves the collapse of an especially extended star where material continues feeding the newly formed compact object for an unusually long period. Another invokes prolonged magnetic activity from a newborn neutron star. Researchers have also considered rare stellar disruptions by black holes for some unusual transients. Distinguishing between these possibilities requires studying the burst spectrum, host galaxy, and later light. The long duration is scientifically valuable because it exposes the behavior of the central engine over a much greater interval than ordinary bursts allow. A phenomenon once defined by its brevity can therefore stretch across a large portion of an observing night. Extreme cosmic events do not always respect the tidy category scientists create to describe them. Gamma-ray burst afterglows can remain detectable long after the main flash. The gamma-ray signal may disappear within seconds, but the explosion can keep announcing itself at other wavelengths for days, weeks, or even months. A relativistic outflow eventually crashes into gas surrounding the source. That collision drives a shock through the material and accelerates charged particles which then radiate across the electromagnetic spectrum. X-rays may dominate early, followed by optical and radio emission that fades more gradually. This afterglow gives astronomers far more information than the primary burst alone. Its spectrum can reveal the distance to the event. Its changing brightness can expose the shape of the jet and the density of the surrounding environment. Sudden changes may indicate additional energy being supplied by the central engine. Radio observations can continue after the optical source becomes too faint to see. Because the afterglow evolves, astronomers often coordinate telescopes around the world to capture different stages. A gamma-ray burst is therefore not merely a momentary flash. Its collision with surrounding space creates a lingering record that can be studied long after the initial explosion has vanished. The brightest recorded gamma-ray burst overwhelmed several space-based detectors. On October 9, 2022, Satellites detected an event so extraordinary that astronomers quickly gave it a memorable nickname. GRB 221009A became known as the boat, meaning the brightest of all time. Its gamma radiation was intense enough to saturate instruments designed specifically for powerful cosmic flashes. Even detectors that were not built primarily for gamma-ray astronomy noticed effects from the event. The burst came from billions of light-years away. Yet its jet happened to be directed exceptionally close to Earth's line of sight. That favorable alignment dramatically amplified its apparent brightness. Researchers studied the event across the electromagnetic spectrum and found evidence linking it to the collapse of a massive star. The burst also affected Earth's ionosphere despite the enormous distance separating us from the source. Statistically, an event this bright in our sky may be exceptionally rare on human timescales. Its detection gave astronomers an unprecedented laboratory for studying relativistic jets, while also demonstrating how strongly orientation can transform the appearance of a distant explosion. Extreme cosmic explosions may briefly ionize parts of planetary atmospheres. High-energy radiation does not need to strike a planet physically to alter its atmosphere. X-rays and gamma rays can remove electrons from atoms and molecules when they are absorbed high above the surface. If a sufficiently energetic cosmic explosion occurs nearby, this ionization can temporarily change atmospheric chemistry. On Earth, strong gamma-ray events have measurably disturbed the ionosphere, even when their sources were located far beyond the solar system. A much closer explosion could produce larger effects. Researchers model how intense radiation might alter ozone concentrations and allow additional ultraviolet light to reach the ground afterward. The severity would depend heavily on distance, beam direction, atmospheric composition, and the energy spectrum of the event. This does not mean gamma-ray bursts routinely threaten inhabited worlds. The dangerous combination of proximity and alignment should be uncommon. Still, the physics introduces a fascinating connection between stellar catastrophes and planetary environments. A world may never encounter the debris of an explosion, yet radiation alone can reach across space and temporarily change the chemistry of the air surrounding it. Distant gamma-ray bursts illuminate gas from the universe's earliest eras. A gamma-ray burst can act like a temporary searchlight behind material that would otherwise be extremely difficult to examine. When the burst's afterglow passes through gas on its way to Earth, atoms absorb very specific wavelengths. Astronomers spread the incoming light into a spectrum and identify those missing portions. Each absorption feature reveals something about material lying between the explosion and us. For very distant bursts, that material can belong to an era when the first generations of galaxies were transforming the universe. Researchers can investigate chemical abundances and measure how much neutral hydrogen remained in intergalactic space. The technique is especially powerful because a burst can briefly outshine its host galaxy by an enormous factor. Unlike quasars, these sources do not remain active for millions of years, so they probe environments associated with individual massive stars. Catching them requires speed because the useful light fades rapidly. For a short period, however, the death of one remote star can backlight billions of light-years of cosmic history and expose matter that would normally remain almost invisible. Astronomers use fading afterglows to locate otherwise invisible cosmic explosions. The initial gamma-ray detection often tells astronomers only that something happened within a broad patch of sky. To learn where the event actually occurred, they hunt for its rapidly fading afterglow. X-ray telescopes can narrow the position first. Optical observatories then search for a new point of light that was absent from earlier images. Once the source is identified precisely, astronomers can determine whether a host galaxy lies beneath it. That step can transform an anonymous burst into a physical event with a distance and environment. Sometimes the host is astonishingly faint and becomes visible only after the afterglow has nearly disappeared. In other cases, the explosion occurs well outside the brightest region of its galaxy, offering clues about the object that produced it. Researchers compare images taken at different times to separate the transient from constant background sources. This pursuit has turned fading light into a form of cosmic detective work. The explosion itself may be impossible to resolve directly, but its disappearing afterglow points back toward the exact place where the catastrophe occurred. A tidal disruption event begins when a star approaches too closely. Most stars can orbit a massive black hole safely for immense periods, provided they stay far enough away. Trouble begins when an unlucky orbit carries one inside the black hole's tidal radius. At that distance, the change in gravitational pull across the star becomes stronger than the star's own ability to hold itself together. The critical distance depends on both objects. A larger star can be disrupted farther out while a denser star may survive a closer approach. The star may have reached this dangerous orbit after gravitational encounters with other stars altered its path over millions of years. Nothing needs to strike the black hole directly. The encounter is purely gravitational. Once disruption begins, the star's previously orderly structure rapidly unravels and its material follows a range of new trajectories. Astronomers search galactic centers for the resulting flares because many central black holes are normally inactive. A single misplaced star can suddenly reveal an object that had remained almost completely dark despite outweighing millions of suns. Black hole gravity can stretch a doomed star into a long stream. Near a black hole, gravity changes significantly over surprisingly short distances. During a close stellar encounter, the side of the star facing the black hole feels a stronger pull than the side farther away. At the same time, the star is squeezed in directions perpendicular to its orbit. The combined deformation can stretch the star into an extraordinarily elongated stream of gas. This process is sometimes called spaghettification, although the underlying physics is the more precise idea of tidal force. The star's original spherical shape disappears as different regions acquire different orbital energies. Some gas races ahead while other material trails behind. Computer simulations show streams wrapping around the black hole before colliding with themselves and beginning to circularize. Those collisions convert orbital motion into heat and help build an accretion flow. What began as an intact star can therefore become a structure extending far beyond its original diameter. The destruction is not caused by the black hole touching the star. Gravity alone pulls different parts of the same object onto radically different paths. Only part of a shredded star may fall into the black hole. Being torn apart by a black hole does not necessarily mean every piece of the star is consumed. During disruption, different portions of stellar material receive different amounts of orbital energy. Roughly speaking, some debris becomes more tightly bound to the black hole while some receives enough energy to escape. The bound material travels away on elongated paths before returning toward the point of closest approach. Its return rate strongly influences how the resulting flare evolves. The unbound fraction heads outward instead and can eventually mix with gas in the galactic nucleus. Exactly how much is captured depends on the geometry of the encounter and the star's internal structure. This division produces one of the strangest outcomes imaginable. A black hole can destroy a star completely without actually eating the whole thing. The event transforms the star into separate populations of debris with entirely different futures. By measuring the changing luminosity of tidal disruption flares, astronomers try to infer how rapidly the bound material falls back. The star disappears as a coherent object, but much of its substance can survive the encounter. Escaping stellar debris can be flung back into interstellar space. The material that avoids capture during a tidal disruption does not simply remain parked beside the black hole. Some of it can leave the encounter traveling at tremendous speed. Because different parts of the original star acquire different energies, unbound gas may be launched outward from the galactic center on trajectories that never return. The escaping stream carries elements that once belonged deep inside a star and can eventually collide with surrounding interstellar material. Those interactions may generate shocks and radio emission long after the brightest phase of the disruption. Researchers are studying whether such debris could contribute meaningfully to the unusual environments around central black holes. Its chemical composition also contains information about the destroyed star. If deeper stellar layers become exposed, spectra might reveal products of nuclear processing that would normally remain hidden inside the star. A tidal disruption event, therefore, does more than feed a black hole. It can redistribute stellar material into its host galaxy. One close gravitational encounter separates the star into matter destined for darkness, and matter thrown outward into a completely new existence. Tidal disruption flares can reveal black holes inside otherwise quiet galaxies. Many galaxies contain massive central black holes that are remarkably difficult to detect. If little gas is falling inward, the black hole produces almost no radiation of its own. It may sit dormant for centuries or much longer while stars orbit nearby. Then one star wanders into danger. The resulting disruption supplies a sudden reservoir of material, and the galactic nucleus brightens dramatically. Astronomers can discover these flares through optical surveys, ultraviolet telescopes, or X-ray instruments. The light usually evolves over months rather than remaining constant like a persistently active galactic nucleus. That temporary behavior helps identify the event. Once recognized, the flare can provide information about the mass of the central black hole and the physics of matter falling toward it. This technique is especially useful in galaxies where ordinary observations give little evidence of nuclear activity. A black hole that cannot be seen directly may therefore expose itself through a single unlucky star. For astronomers, the victim becomes a beacon, announcing the presence of an otherwise hidden gravitational giant. Some shredded stars produce powerful jets aimed across intergalactic space. Most tidal disruption events glow because stellar debris heats as it settles around a black hole. A rare few do something much more dramatic. They launch relativistic jets from the galactic center. One famous example was discovered in 2011 when a source named Swift J1644+57 erupted in X-rays and remained violently variable. The leading explanation was a star being disrupted by a massive black hole while a jet happened to point roughly toward Earth. Exactly how such jets form is still under investigation. Strong magnetic fields threading the newly created accretion flow are probably important. The jet can transport energy far beyond the immediate region of the destroyed star and generate radio emission as it encounters surrounding gas. Because relativistic beaming greatly enhances a jet viewed head-on, only a small fraction of jetted disruptions should look spectacular from Earth. These events combine two extremes in one system. A star is torn apart by gravity. Then some of the energy released by its destruction is channeled into matter moving almost as fast as light. A black hole may repeatedly strip matter from the same surviving star. Not every close encounter ends with total destruction. A star can pass near a black hole, lose only part of its outer layers, and then escape on a highly elongated orbit. If that orbit remains bound, the star eventually returns. Each close passage can remove more material and create another flare. Astronomers have identified repeating nuclear transients that may be produced by this partial tidal disruption process. Their recurrence offers something rare in transient astronomy. Instead of seeing a catastrophe only once, researchers may watch the same star return to danger again and again. The timing between outbursts provides information about the surviving orbit, while changes in brightness can reveal how the star is evolving after each encounter. Repeated stripping may eventually destroy it completely or alter its structure enough to change the pattern. In some scenarios, only the star's extended envelope is vulnerable while its denser core survives. A black hole can therefore behave less like a single fatal trap and more like a gravitational machine that removes pieces of the same star over successive passages. White dwarfs can also be torn apart by intermediate black holes. A white dwarf is extraordinarily compact, so an ordinary supermassive black hole may swallow a hole before tidal forces can destroy it outside the event horizon. A smaller black hole changes that calculation. Intermediate mass black holes are thought to occupy the gap between stellar mass objects and the giants found in galactic centers. If one encounters a white dwarf, the tidal radius can lie safely outside the horizon. The compact star may then be pulled apart before crossing the point of no return. The encounter could compress and heat the white dwarf strongly enough to trigger nuclear burning in some circumstances, potentially producing an unusual explosive transient. Detecting such an event would be exciting for another reason. Intermediate mass black holes have been notoriously difficult to confirm. A disrupted white dwarf could provide a distinctive sign of their existence in dense star clusters or dwarf galaxies. The victim's density effectively becomes a measuring tool. Only a black hole within the appropriate mass range can tear this kind of stellar remnant apart where the destruction remains visible. Tidal forces grow dramatically across the event horizon of smaller black holes. The event horizon is famous because nothing inside it can escape. But the experience of approaching that boundary depends strongly on the black hole's mass. For a stellar mass black hole, the horizon is relatively small. Gravity therefore changes very rapidly across the length of a human body or any other extended object near it. The resulting tidal forces can become destructive before the horizon is reached. Around a supermassive black hole, the situation is surprisingly different. Its horizon is much larger, so the gravitational gradient at the boundary can be far gentler. An object could theoretically cross the horizon of a sufficiently massive black hole without being immediately torn apart at that exact location. Destruction would still follow deeper inside. This distinction reveals why black holes cannot be understood by surface gravity alone. The important quantity for stretching an object is how quickly gravity changes from one point to another. Smaller black holes can therefore be more violently disruptive near their horizons than far heavier ones despite possessing dramatically less total mass. Supermassive black holes can swallow stars before tearing them apart outside. There is a point where making a black hole more massive actually makes visible tidal disruption less likely. As the black hole grows, Its event horizon expands faster with mass than the tidal disruption distance does. Above a certain scale, a sun-like star can cross the horizon while still largely intact. Any later destruction occurs where its light can never escape. Astronomers sometimes call the approximate dividing mass the Hills mass, although the exact value depends on the star and on whether the black hole is spinning. Spin can change the size and geometry of the relevant boundaries, allowing disruptions around somewhat heavier objects in certain orientations. This creates a useful observational clue. If astronomers confidently identify a tidal disruption flare from a very massive galactic nucleus, the event can potentially constrain the black hole's properties. The absence of flares at the highest masses also has a physical explanation. The black hole has not become too weak to destroy stars. Its horizon has simply grown so large that the crucial destruction disappears from the observable universe. Merging black holes radiate several suns' worth of mass as gravitational waves. During the final moments of a black hole merger, an extraordinary fraction of the system's mass can leave without becoming matter or light. Einstein's equation linking mass and energy allows part of the total mass to be converted into gravitational radiation. In the first directly detected merger, the two original black holes had masses of roughly 36 and 29 suns. The final black hole contained about 62 solar masses. Around 3 suns' worth of mass had effectively been carried away as gravitational wave energy. The conversion occurred mainly during the violent final stage of the collision. For a brief moment, the power emitted in gravitational waves exceeded the combined light output of the visible universe, even though the event itself may have produced almost no light. This does not mean 3 actual stars were destroyed. Mass already present in the orbiting black holes was converted into energy through the changing gravitational field. Measuring that missing mass lets physicists test numerical predictions of general relativity under some of the strongest gravitational conditions nature provides. The final black hole can recoil from its galaxy after merging. A newly merged black hole does not always remain exactly where the collision occurred. Gravitational waves can carry momentum as well as energy. If those waves are emitted more strongly in one direction than another, the final black hole must move the opposite way to conserve momentum. This gravitational recoil is often called a kick. Simulations show that some configurations can produce velocities of thousands of kilometers per second. In smaller galaxies, a sufficiently strong kick could launch the black hole completely out of the system. A weaker recoil might leave it oscillating through the galactic center before eventually settling again. Astronomers search for possible examples by looking for active black holes whose positions or velocities differ from those of their host galaxies. Confirming a recoiling supermassive black hole is difficult because other processes can imitate some of the same signatures. Yet the predicted effect is a remarkable consequence of wave emission. 2 invisible objects can merge, send spacetime ripples unevenly across the cosmos, and propel the resulting black hole through space like an enormous gravitational rocket. Unequal mergers produce stronger gravitational kicks than balanced collisions. The strength of a recoil depends on how asymmetrical the merger becomes. If 2 identical non-spinning black holes approach in a perfectly symmetric configuration, their gravitational wave emission can balance so that little net momentum is carried away. Change the masses, however, and the symmetry breaks. One black hole moves differently from the other, creating a more uneven radiation pattern and a larger kick. Spin can amplify the effect dramatically, especially when the 2 spin directions are arranged unfavorably relative to the orbit. Numerical relativity simulations explore these configurations by solving Einstein's equations on powerful computers. They show that the most extreme recoils require particular combinations of spin and orbital geometry rather than mass difference alone. Understanding these kicks matters for galaxy evolution. Small early galaxies may have struggled to retain growing black holes if mergers frequently launched the remnants away. The black holes seen at the centers of massive galaxies today therefore carry a hidden history of which mergers they survived. A slight imbalance during a collision can influence whether a galactic nucleus keeps its central black hole at all. Some recoiling black holes may wander far beyond their galactic centers. If a merger gives a black hole a substantial kick without ejecting it completely, the object can begin a long journey through its host galaxy. Instead of sitting in the nucleus, it may travel thousands of light years away before gravity turns it back. Repeated passages gradually lose energy through interactions with surrounding stars and matter, eventually drawing the black hole toward the center again. The process can take a very long time. During its wandering phase, the black hole might carry a tightly bound cluster of stars or a small amount of accreting gas with it. Those companions could make the displaced object detectable. Researchers search for unusual compact star clusters and off-center active galactic nuclei as possible evidence. A wandering massive black hole would challenge the familiar picture of every galaxy having its largest black hole fixed neatly at the center. Galactic nuclei can be dynamically messy places. A merger occurring millions of years earlier may leave its central object roaming through the galaxy long after the gravitational waves themselves have passed Earth. Black hole mergers can finish within a fraction of 1 second. The final stage of a stellar mass black hole merger unfolds faster than the events leading to it can easily be imagined. The binary may have existed for millions or billions of years. During its last moments within the sensitive band of ground-based gravitational wave detectors, however, the orbital frequency rises rapidly. The black holes circle each other faster as their separation shrinks, producing the characteristic increase in frequency called a chirp. Near merger, they can complete multiple orbits in fractions of a second. Their separate event horizons then combine and settle into one distorted remnant. For heavier black holes, the relevant timescales are longer because the entire system is physically larger. Stellar mass mergers are extraordinarily quick. This brevity is why gravitational wave observatories record some signals as short sweeping pulses rather than long astronomical events. Sophisticated computer models are required to reconstruct what happened from those fleeting vibrations. A binary can spend almost its entire existence approaching catastrophe, then complete the most violent part of its history before a human listener could say the word collision. Their final gravitational wave signal is called a ring-down. After two black holes merge, the newborn object is not immediately a perfectly settled black hole. Its horizon has been violently distorted by the collision. Like a struck bell, the remnant responds by oscillating in characteristic patterns while radiating away those distortions as gravitational waves. This final stage is called the ring-down. The analogy is useful because a bell's tone depends on its shape and material, while a black hole's allowed vibration frequencies depend on its physical properties. The signal fades rapidly as the object settles toward a stable state described by general relativity. Ring-down waves are weaker than the loudest part of the merger, which makes them challenging to measure precisely. Future detectors should observe them with much greater clarity. Scientists are especially interested in determining whether several distinct vibration modes can be identified. If their frequencies match the predictions for a black hole, the result would provide a demanding test of Einstein's theory. The last vibrations of a collision, therefore, contain information about whether the final object behaves exactly as a black hole should. Ring-down vibrations reveal the mass and spin of the newborn black hole. General relativity makes an extraordinary prediction about settled black holes. Once surrounding disturbances have disappeared, an isolated astrophysical black hole can be described mainly by its mass and angular momentum, plus electric charge that should be negligible for realistic cosmic examples. Its ring-down frequencies therefore act like a fingerprint. Measure the pitch and damping of the gravitational wave oscillations and physicists can infer the mass and spin of the remnant. Detecting multiple ring-down modes would offer an even more powerful test. All of them should point toward the same black hole properties. If they did not, researchers would need to investigate whether the discrepancy came from measurement uncertainty or from physics beyond the standard description. This program is sometimes compared with spectroscopy because scientists are identifying characteristic modes much as astronomers identify chemical elements through spectral lines. The difference is striking. Instead of analyzing light from atoms, they analyze vibrations in spacetime itself. A black hole produces no solid surface sound. Yet its gravitational ringing can reveal precisely what kind of object the merger created. Supermassive black hole binaries may distort spacetime across entire galaxies. When galaxies merge, their central black holes can eventually form a binary whose orbit spans distances vastly larger than those of stellar mass systems. Such enormous pairs move slowly, so the gravitational waves they produce have extremely low frequencies. A single wave cycle can take years or decades. Detectors on Earth cannot measure these signals with kilometer-long laser arms because the wavelengths are far too enormous. Astronomers instead use the Milky Way itself as part of the experiment. Millisecond pulsars scattered across the galaxy serve as exceptionally stable clocks. If a long gravitational wave passes between Earth and those pulsars, it slightly alters the arrival times of their radio pulses. The effect is tiny, but monitoring many pulsars for years can reveal correlated patterns across the sky. In this sense, the detector becomes galactic in scale. The signals may originate from pairs of supermassive black holes orbiting in galaxies hundreds of millions of light-years away. A collision process in one galaxy can therefore be measured through subtle timing changes distributed across another. Pulsar timing has revealed a low-frequency gravitational wave background. After years of watching some of the most stable pulsars in the sky, several international collaborations reported compelling evidence for a shared gravitational signal at nanohertz frequencies. Researchers did not detect one sharp merger like ground-based observatories do. Instead, they found slow variations in pulsar timing that show the kind of spatial correlation expected from a background of gravitational waves. Different pulsars are affected in related ways depending on their angular separation in the sky. Detecting that pattern required observations stretching across many years because each wave changes extraordinarily slowly. The result opened a completely different gravitational wave window from the one used to study stellar mass black hole mergers. Scientists can now investigate processes operating on scales that were previously inaccessible. Continued measurements should sharpen the background signal and may eventually reveal individual exceptionally massive binaries above it. Pulsars discovered as exotic stellar remnants have become components of a galaxy-sized gravitational observatory. Their regular radio flashes allow humanity to sense space-time changes whose periods are comparable to large fractions of a human lifetime. That background may come from countless merging supermassive black hole pairs. The leading explanation for the newly measured nanohertz gravitational wave background is not a single enormous source. It is the combined murmur of many supermassive black hole binaries throughout the universe. Galaxy mergers should naturally bring central black holes together. After the galaxies combine, the two black holes sink toward the new center and begin orbiting one another. Across cosmic history, enormous numbers of systems may have reached this stage. Their individual waves overlap by the time they reach Earth, creating a persistent background rather than easily separated signals. The exact strength and shape of that background can reveal how frequently galaxies merge and how efficiently their black holes move toward final coalescence. It may even expose whether interactions with stars or gas alter those orbits. As pulsar timing measurements improve, astronomers hope the smooth background will begin resolving into particularly loud individual binaries. What currently sounds like one collective gravitational hum may eventually separate into identifiable systems. The universe could be filled with giant black hole pairs slowly approaching mergers that will not finish for thousands or millions of years. Galaxies can collide without most of their stars ever touching. A collision between two galaxies sounds as though billions of stars should smash together. In reality, direct stellar impacts are extraordinarily unlikely because galaxies are mostly empty space. Even in crowded regions, the distances between stars are enormous compared with their sizes. When two galaxies pass through one another, their stars usually continue along altered paths without physically colliding. Gravity does the real damage. Each galaxy pulls on the other and changes the orbits of countless stars at once. Some stars are pushed into wider paths. Others are thrown into long streams that extend far beyond the original galaxies. Gas behaves differently because clouds can strike and compress as the systems overlap. The entire encounter may last hundreds of millions of years with the galaxies passing through each other more than once before finally settling. From a distance, the result can look violently tangled. On the scale of individual stars, however, most of the participants never come remotely close to touching. Two vast stellar systems can therefore pass through one another, while collisions between actual suns remain almost non-existent. Galactic collisions reshape spiral arms over hundreds of millions of years. A spiral galaxy does not keep the same elegant shape forever. When another galaxy approaches, its gravity can pull strongly on the disk and distort the pattern of stars. Spiral arms may stretch, bend, or become much more prominent as the encounter develops. In some cases, a close passage creates broad bridges of material between the galaxies. Other regions are drawn outward into sweeping structures that can remain visible long after the closest approach. The transformation unfolds slowly by human standards, yet it can completely change the appearance of both galaxies. Computer simulations allow astronomers to run these interactions forward and compare the resulting structures with real systems seen through telescopes. By adjusting the masses and trajectories, researchers can reconstruct how particular distorted galaxies may have formed. A graceful spiral can become irregular during the encounter and later settle into a very different configuration. Galactic architecture is therefore not fixed. The shapes seen in astronomical photographs are temporary stages in a gravitational history that may include repeated encounters stretching across billions of years. The Milky Way is currently consuming several smaller neighboring galaxies. Our home galaxy is not growing in complete isolation. Smaller satellite galaxies orbit the Milky Way and some are gradually being pulled apart by its gravity. The Sagittarius dwarf spheroidal galaxy provides a striking example. As it repeatedly passes around the Milky Way, stars are stripped from it and stretched into enormous streams that wrap through the galactic halo. Astronomers can identify these former members by measuring their motions and chemical compositions. Other stellar streams reveal the remains of systems that were disrupted much earlier. This process is known as galactic cannibalism, though it happens through gravity rather than anything resembling ordinary feeding. The smaller galaxy slowly loses its identity as its stars become mixed into the larger one. Evidence from the Milky Way's halo suggests that many such mergers have occurred during its history. Some stars near us may even have been born in entirely different galaxies before being absorbed. The Milky Way therefore contains a record of past collisions written into the movements and chemistry of stars now considered part of our own galaxy. Andromeda and the Milky Way are moving toward a future merger. The largest neighboring spiral galaxy is approaching us rather than receding with cosmic expansion. Measurements of Andromeda's motion show that the two galaxies are gravitationally bound and are expected to interact several billion years from now. The exact sequence remains uncertain because small differences in sideways motion can change the encounter. Current models generally predict at least one close passage followed by a gradual merger. The night sky would look extraordinary during the approach because Andromeda would appear increasingly large as its stars spread across a wider region. Earth itself would not necessarily be endangered by direct stellar collisions. The greater change would be to the structure of both galaxies. Their disks could become severely distorted before the combined system eventually settles into a new form. The Sun may be thrown onto a different galactic orbit during the process. Humanity will almost certainly face many other cosmic changes long before then. Even so, the prediction reminds us that the Milky Way is part of a dynamic local environment. Our galaxy has a future that includes another giant system. Colliding galaxies can trigger enormous bursts of new star formation. When galaxies interact, their gas can respond far more dramatically than their stars. Gravitational forces disturb huge reservoirs of cold material and drive clouds into denser regions. Once enough gas becomes compressed, gravity can cause many new stars to form at nearly the same time. Astronomers call particularly intense episode starbursts. Some interacting galaxies produce stars at rates far above those of calm spiral systems. The effect is especially striking in the antennae galaxies, where enormous young star clusters have formed during an ongoing merger. Many of those clusters contain thousands or even millions of stars. The encounter does not create the raw material from nothing. It rearranges gas that was already present and pushes part of it across the threshold needed for gravitational collapse. Infrared telescopes are especially useful because newborn stars often remain hidden inside thick dust. A galactic collision can therefore look destructive on the largest scale, while simultaneously creating vast numbers of new suns. The same interaction that tears apart familiar structure can produce one of the most productive periods in a galaxy's life. Gas clouds collide far more often than stars during galactic mergers. Stars behave almost like isolated particles when galaxies overlap, but interstellar gas occupies a much greater fraction of the available space. Huge clouds can therefore run into one another as two galactic disks pass through the same region. These collisions create shocks that heat some gas and compress other portions into dense layers. The gas also loses orbital energy more readily than stars because it can radiate heat away. As a result, large amounts of material may flow toward the center of the merging system. That inward movement can feed intense star formation or supply gas to a central black hole. Astronomers map molecules such as carbon monoxide to follow the cold material and compare it with hotter gas observed at other wavelengths. The patterns reveal where compression is strongest and where new stellar nurseries may develop. This difference between gas and stars is crucial for understanding mergers. A galaxy is not merely a collection of suns. Its diffuse material responds through pressure and collisions, which means two galaxies can pass through one another while their gas undergoes an entirely different and far more turbulent experience. Some galaxy collisions create long tidal tails containing billions of stars. One of the most spectacular signatures of a galactic encounter can extend far beyond the galaxies themselves. During a close passage, gravity pulls more strongly on the nearer sides of each system and can stretch material into enormous tidal tails. These structures may reach hundreds of thousands of light years into space. They contain stars that once belonged securely to the galactic disks along with gas drawn outward during the same encounter. The tails can survive for a surprisingly long time because the stars continue following related gravitational paths. Their shapes preserve clues about how the collision unfolded. Astronomers can compare real tidal structures with computer simulations to estimate the direction and timing of previous encounters. Some tails also contain active regions of star formation where compressed gas has become dense enough to collapse. The mice galaxies and the antennae galaxies display dramatic examples of these extended features. A galaxy can therefore have part of its stellar population pulled into a structure far larger than its original disk. Gravity turns an encounter into a record that stretches visibly across intergalactic space. Entire dwarf galaxies can form inside debris from larger galactic collisions. A galactic collision can sometimes create a new galaxy from material ripped out of older ones. Tidal tails contain gas and stars drawn away during the encounter. In certain regions, gravity can gather enough of that debris into a self-bound object. The result is called a tidal dwarf galaxy. Unlike many ordinary dwarf galaxies, these objects form from material that has already been chemically enriched inside larger galaxies. Their gas therefore contains more heavy elements than might be expected for a newly assembled system of similar size. Another intriguing difference concerns dark matter. Standard models predict that most of the original galaxy's dark matter remains in extended halos, rather than being efficiently pulled into narrow tidal tails. Tidal dwarfs may therefore contain relatively little of it. Researchers study these systems because they provide unusual tests of galaxy formation and gravitational dynamics. Their very existence shows that galaxies are not created only from pristine material early in cosmic history. Under the right circumstances, fragments torn from mature galaxies can gather themselves into new gravitationally bound systems during the aftermath of a collision. Supermassive black holes may merge after their host galaxies combine. When two large galaxies merge, each may bring a central black hole containing millions or billions of solar masses. The galaxies can settle into one system long before their black holes finish their own journey. At first, the two massive objects move through a crowded sea of stars. Gravitational interactions rob them of orbital energy and pull them toward the center. Eventually, they can form a bound pair. Bringing them even closer requires further interactions with stars or surrounding gas. The final stage occurs when gravitational radiation becomes efficient enough to drive the black holes rapidly inward. This sequence can take hundreds of millions of years or longer. Astronomers are actively searching for galaxies that contain pairs of active nuclei as evidence for different stages of the process. Some systems show two bright centers separated by thousands of light years. Others may contain much tighter binaries that are harder to resolve. A galaxy merger therefore has an ending hidden inside its center. Long after the larger stellar structures have blended together, the two original central black holes may still be approaching their own collision. Galaxy cluster collisions separate hot gas from invisible dark matter. A galaxy cluster contains far more than the galaxies visible in ordinary photographs. Enormous quantities of hot gas fill the space between them, and most of the total mass appears to be dark matter. When two clusters collide, these components behave differently. The galaxies mostly pass through one another because direct collisions are rare. Dark matter also appears to move through with relatively little resistance. The hot gas does not. Gas from the two clusters crashes together and slows because electromagnetic interactions create pressure and shock heating. Astronomers can map the gas through its X-ray emission. They can separately map the overall gravitational mass using gravitational lensing, which measures how background light is distorted. In some merging clusters, the two maps do not line up. The dominant mass moves ahead while much of the ordinary hot gas remains behind. This separation gives scientists a remarkable natural experiment. A single cosmic collision pulls different forms of matter apart enough that their behavior can be studied independently on scales far beyond anything possible in a laboratory. The bullet cluster provides striking evidence for dark matter's gravitational presence. Among the most famous colliding galaxy clusters is a system known as the bullet cluster. Its importance comes from the mismatch that can be mapped directly. X-ray observations show where most of the ordinary matter lies because the collision has concentrated hot gas near the region where the clusters pass through each other. Gravitational lensing tells a different story. The strongest concentrations of mass are displaced from that gas and remain closer to the galaxies on either side. Since the galaxies themselves contain far too little visible matter to account for the gravitational signal, another massive component appears to have traveled through the collision without slowing like ordinary plasma. Dark matter provides the standard explanation. The observation does not reveal what dark matter is made from, but it strongly constrains theories that attempt to explain galaxy cluster gravity using ordinary matter alone. Other merging clusters provide additional tests. Yet the bullet cluster remains especially clear. Nature effectively separated most of the visible material from most of the gravitating mass, allowing astronomers to compare them in the same object. Cluster mergers can generate shock waves spanning millions of light years. Galaxy clusters are the largest gravitationally bound structures in the universe, so collisions between them involve staggering amounts of energy. As two clusters approach, their vast clouds of hot gas can meet at speeds of thousands of kilometers per second. The collision drives shock fronts through plasma that already reaches temperatures of millions of degrees. Some shocks extend across distances comparable to or larger than entire galaxies. X-ray telescopes reveal abrupt changes in gas temperature and density that mark the moving fronts. Radio observatories can also detect enormous diffuse structures known as relics, which often trace regions where particles have been accelerated by merger shocks. Unlike the sharp blast from a stellar explosion, a cluster shock evolves over hundreds of millions of years. Its scale is almost impossible to reproduce mentally. Light itself may take millions of years to cross the affected region. These events demonstrate that cosmic violence is not limited to compact objects. Whole collections of thousands of galaxies can collide and send pressure waves through volumes of space large enough to engulf the Milky Way many times over. Cosmic collisions can accelerate particles to energies beyond human-built machines. The universe contains natural particle accelerators vastly larger than anything constructed on Earth. Shock waves and powerful magnetic fields generated by supernova remnants, galaxy clusters, and relativistic jets can repeatedly scatter charged particles. Each interaction may increase a particle's energy until it travels at a speed extremely close to light. The exact acceleration mechanisms vary, and researchers still debate which sources dominate at the highest energies. One widely studied process is diffusive shock acceleration. Charged particles cross back and forth through a shock front while magnetic turbulence redirects them, allowing repeated energy gains. Because astrophysical shocks can span enormous distances and persist for long periods, they can push particles far beyond the energies achieved in terrestrial accelerators. These particles eventually escape and may travel through interstellar or intergalactic space before encountering matter elsewhere. Their paths are bent by magnetic fields, which makes their origins difficult to trace. A cosmic collision can therefore become a machine for launching individual atomic nuclei across the universe with energies that human technology has never directed produced. Fast radio bursts release immense radio energy within mere milliseconds. For only a few thousandths of a second, a distant source can become one of the brightest radio objects in the sky. Fast radio bursts were first recognized after astronomers found an unusual pulse in archived telescope data. Since then, large surveys have detected hundreds of sources. The bursts are extremely brief, yet some release as much radio energy in that instant as the sun produces across many days at all wavelengths. Their short duration shows that the emitting region must be compact. A source cannot vary coherently faster than light can cross the region responsible for the change. The first bursts were difficult to interpret because radio telescopes often provided only rough positions. Newer instruments can now localize some events to individual host galaxies. That breakthrough proved that many originate far beyond the Milky Way. Their causes may not all be identical. Several physical mechanisms could produce intense coherent radio emission under extreme magnetic conditions. Whatever the detailed explanation, these signals demonstrate that a tiny region of space can release an astonishingly concentrated flash of radio energy and then vanish almost immediately. Some fast radio bursts repeat while others appear only once. The discovery that certain fast radio burst sources fire again transformed the mystery. A repeating source cannot be explained by any event that completely destroys its engine during the first burst. Some repeaters have produced dozens or even hundreds of pulses with intervals ranging from seconds to months. Their individual bursts can differ in brightness and duration. In several cases, periods of activity appear to follow longer cycles, although the reasons remain uncertain. Other fast radio burst sources have never been observed to repeat despite extensive monitoring. That distinction may mean there are several classes of physical origin. It may also reflect observational limits because a supposedly one-off source could simply repeat too faintly or too rarely for existing telescopes to catch. Astronomers compare burst shapes and local environments to search for patterns. Some repeaters occupy regions with persistent radio emission nearby while others do not. The field remains wonderfully unsettled. Two flashes that look similar in a telescope may come from related engines behaving differently or from entirely separate cosmic processes capable of producing the same brief radio signature. Magnetars are a leading explanation for many repeating fast radio bursts. A magnetar contains exactly the sort of extreme ingredients that could produce a powerful radio flash from a very small region. Its immense magnetic field stores huge amounts of energy, and sudden rearrangements can accelerate charged particles rapidly. Researchers have developed several models in which magnetic activity launches disturbances into the surrounding environment or directly produces coherent radio emission near the star. The repeating nature of many fast radio burst sources fits naturally because a magnetar can remain active after each outburst. Young magnetars may be especially promising if they are surrounded by dense material left from their formation. That environment could help explain why some repeaters show complicated radio behavior. Not every detail is solved. Astronomers still debate exactly where the radio waves are generated, and why only some magnetars appear capable of producing exceptionally luminous bursts. Different fast radio burst populations may also require different explanations. Even so, magnetars provide a compelling connection between the strongest known stellar magnetic fields and some of the shortest, brightest radio events detected across cosmological distances. One galactic magnetar produced a radio burst resembling distant cosmic signals. In April of 2020, astronomers received the clue they had been waiting for. A magnetar within the Milky Way called SGR 1935+2154 produced an intense burst of radio waves. Viewed from another galaxy, the signal would have resembled a relatively faint fast radio burst. X-ray instruments detected high-energy activity at nearly the same time, strengthening the connection with magnetar outbursts. This was the first direct demonstration that a known magnetar could generate a radio flash approaching the extraordinary class previously detected mostly at extragalactic distances. The event did not prove that every fast radio burst comes from a magnetar. It showed that magnetars can produce at least some of them. Researchers studied the timing and structure of the pulse in extraordinary detail because the source was far closer than typical fast radio bursts. The discovery turned a broad theoretical possibility into an observed physical link. A mysterious phenomenon first discovered far beyond our galaxy suddenly had a recognizable relative living inside the Milky Way. Fast radio bursts reveal hidden matter between galaxies through their delays. A fast radio burst carries information not only about its source, but also about every cloud of ionized matter encountered on the journey to Earth. Lower radio frequencies travel through free electrons slightly more slowly than higher frequencies. As a result, the burst arrives spread across time in a predictable pattern. Astronomers measure this effect through a quantity called dispersion measure. Part of the delay comes from electrons in the Milky Way. Additional contributions can arise in the host galaxy and near the source. What remains can trace the otherwise difficult-to-detect material between galaxies. This is important because much of the universe's ordinary matter is thought to reside in diffuse gas that is extremely faint. By combining a burst's dispersion with its independently measured distance, researchers can estimate how many electrons lie along the line of sight. A population of well-localized fast radio bursts can therefore map the distribution of baryonic matter across cosmic space. A millisecond radio flash becomes a measuring probe that weighs material too thin and diffuse to glow brightly on its own. Certain bursts travel billions of years before reaching radio telescopes. By the time a distant fast radio burst reaches Earth, the galaxy that produced it may have changed enormously. Radio waves from some sources have traveled for billions of years across an expanding universe before striking a telescope for only milliseconds. During that journey, cosmic expansion stretches the wavelength of the signal. Intervening plasma also alters its arrival pattern. Astronomers can identify a host galaxy for well-localized bursts and measure its redshift, allowing them to connect the observed pulse with a specific period in cosmic history. Particularly distant examples give researchers a way to study how intergalactic matter evolved over time. The contrast in timescales is extraordinary. The source may have emitted its defining signal in a fraction of a heartbeat. Yet the radiation then spent a significant portion of the universe's history traveling toward us. It crossed enormous regions of space while stars formed and died elsewhere. Radio astronomy compresses that entire journey into one brief trace on a detector. A momentary event can arrive carrying information gathered across billions of light years. Cosmic rays strike Earth with energies exceeding the largest particle accelerators. Earth is continually bombarded by atomic nuclei and other particles arriving from space. Most cosmic rays have modest energies by astrophysical standards, but a tiny fraction are astonishingly powerful. The most energetic examples carry far more energy in a single particle than the Large Hadron Collider can give to an individual proton. When one strikes the upper atmosphere, it collides with an atomic nucleus and creates a cascade of secondary particles. That air shower can spread across many square kilometers before reaching the ground. Large observatories detect these showers using arrays of particle counters or telescopes that watch faint ultraviolet light produced in the atmosphere. The original cosmic ray itself never reaches the detector intact. Researchers reconstruct its energy and direction from the enormous cascade it creates. These events are rare, especially at the highest energies. Detecting enough of them requires observatories covering vast areas. Nature can somehow accelerate a single atomic nucleus to an energy beyond our most powerful machines, then send it across space until Earth's atmosphere becomes the target that finally reveals its arrival. The most energetic cosmic rays arrive from still mysterious distant sources. Astronomers know that ultra-high energy cosmic rays exist, but tracing them back to their accelerators is exceptionally difficult. Charged particles do not travel through the universe in perfectly straight lines. Galactic and intergalactic magnetic fields bend their trajectories, erasing much of the directional information that ordinary photons preserve. At the highest energies, the deflection becomes smaller, which offers some hope of identifying source regions. Observatories have found hints of associations with certain nearby extragalactic structures, but no single population has yet explained everything convincingly. Possible accelerators include active galactic nuclei and other environments capable of sustaining immense electromagnetic fields. There is another complication. The highest energy particles interact with background radiation during long journeys, which limits how far many of them can travel without losing energy. Their sources therefore cannot all lie arbitrarily far away. Researchers combine arrival directions with measurements of particle composition to narrow the possibilities. Somewhere in the relatively nearby universe, natural machines are accelerating atomic nuclei to extraordinary energies. Yet the identity of those machines remains one of high-energy astrophysics' most persistent mysteries. Active galaxies launch particle jets longer than their host galaxies. At the center of an active galaxy, matter falling toward a supermassive black hole can help create jets that extend far beyond the visible galaxy itself. These outflows may travel for hundreds of thousands or even millions of light years before finally slowing. Radio telescopes reveal enormous lobes where the jets deposit energy into surrounding space. The particles within them radiate strongly as they spiral through magnetic fields. One remarkable system can therefore contain a central engine smaller than the solar system in scale, while producing structures larger than the galaxy hosting it. The jets remain surprisingly narrow over vast distances, which suggests that magnetic fields play a major role in guiding the flow. They can also develop knots and bright hotspots where material encounters resistance. Astronomers study these structures to understand how energy from a galactic nucleus reaches the intergalactic environment. A black hole may be defined by its ability to trap anything crossing its horizon. Yet activity outside that horizon can produce some of the longest coherent structures visible anywhere in the cosmos. Some quasar winds carry enough power to reshape entire galaxies. Quasars are powered by rapidly accreting supermassive black holes, and not all of the infalling material reaches the horizon. Radiation and magnetic processes can drive tremendous winds away from the central region. Spectra reveal gas racing outward at thousands or even tens of thousands of kilometers per second. If enough material participates, the outflow can carry an enormous amount of energy into the host galaxy. Astronomers suspect these winds a one-way black hole growth can influence star formation far beyond the nucleus. Gas compressed by an outflow might form stars in some locations. Elsewhere, the same wind could heat or remove the cold material needed to make future stars. This interaction is known as feedback. Galaxy evolution models often require some form of powerful feedback to explain why the largest galaxies do not convert all of their available gas into stars. A black hole itself occupies a tiny central region. Yet the energy released while it feeds can influence gas thousands of light years away. The consequences of accretion can therefore spread across the entire galaxy. Black hole jets can switch star formation on or off. The energy released around a supermassive black hole can have opposite effects depending on where and how it reaches galactic gas. A powerful jet may plow into a cold cloud and compress it until gravity triggers new stars. Observations have found systems where star formation appears enhanced along the path of a jet. In other environments, the outcome is suppressive. Jets can inflate enormous cavities in the hot gas surrounding massive galaxies and clusters. The injected energy prevents that gas from cooling efficiently enough to settle into new stellar nurseries. Without a fresh supply of cold material, star formation slows. This balancing act is central to modern ideas about galaxy evolution. The black hole does not intentionally regulate anything. Energy released during accretion simply changes the physical conditions around it. Yet the result can resemble a thermostat operating on galactic scales. The same basic engine can encourage new stars in one region while preventing their formation elsewhere. A tiny central object can therefore influence whether enormous reservoirs of gas become future suns or remain hot and diffuse. Blazar outbursts occur when a galactic jet points toward Earth. A blazar is not a completely different kind of galaxy. It is an active galactic nucleus viewed from an extraordinary angle. One of its relativistic jets happens to point almost directly toward us. Because the emitting material moves close to light speed, relativistic effects greatly enhance the observed brightness and make variations appear unusually rapid. A blazar can flare dramatically across radio, optical, X-ray, and gamma-ray wavelengths. Some changes occur on timescales short enough to show that the emitting region is remarkably compact. The radiation is also often strongly polarized, which reveals the influence of organized magnetic fields inside the jet. Astronomers monitor blazars because their violent variability provides a direct view into relativistic plasma behavior. High-energy neutrinos have even been associated with at least one flaring blazar, raising the possibility that these jets accelerate particles to extreme energies. Change the viewing angle and the same object might look much less dramatic. Blazars demonstrate that perspective alone can determine whether a distant galactic nucleus appears ordinary or becomes one of the brightest high-energy sources in the sky. White dwarf mergers may ignite some of the universe's brightest supernovae. Two white dwarfs in a tight binary can spend ages spiraling slowly together before their final encounter. If their combined conditions allow carbon burning to ignite catastrophically, the merger may produce a Type Ia supernova. This double degenerate scenario is one of the leading pathways proposed for these important explosions. The details depend on the masses and compositions of the two remnants. In some mergers, one white dwarf may be disrupted and form a hot structure around the other before ignition. In others, violent compression during the collision itself could trigger burning quickly. Astronomers search for evidence by examining supernova remnants and looking for surviving companion stars. A double white dwarf merger should leave no ordinary donor star nearby. Researchers also measure the abundances of elements created during the explosion because different ignition mechanisms produce different chemical patterns. Understanding the pathway matters far beyond stellar evolution because Type Ia supernovae are used as distance indicators. Some of astronomy's most valuable cosmic rulers may begin when two apparently dead stars finally collide. Colliding white dwarfs could produce explosions without leaving any stellar remnant. A thermonuclear explosion differs fundamentally from a core collapse supernova. Instead of gravity crushing a stellar core into a compact remnant, runaway nuclear burning can release enough energy to unbind a white dwarf completely. When two white dwarfs collide or merge under suitable conditions, carbon and oxygen may ignite across a substantial fraction of the material. Burning races through the dense stellar matter and converts it into heavier nuclei while releasing enormous energy. If the explosion becomes sufficiently powerful, there is no neutron star left behind because the original white dwarfs were never massive stellar cores undergoing gravitational collapse. Their matter is simply dispersed. Astronomers test this picture by searching old supernova remnants for compact central objects. The absence of one is consistent with a thermonuclear origin. The expanding debris eventually mixes into interstellar space and enriches future generations of stars with elements such as iron. Two stellar corpses can therefore meet long after their original stars have faded and experience a second ending so complete that neither survives the encounter as a bound object. Stars can collide directly inside the crowded centers of dense clusters. Direct stellar collisions are rare across most of a galaxy, but the situation changes inside exceptionally dense star clusters. Near the center, thousands or millions of stars may occupy a relatively small volume and continually pass one another on complicated orbits. Over long periods, chance encounters can become close enough for stars to touch or merge. Gravity can also focus their trajectories and increase the effective collision rate. The result may create a star more massive than would normally be expected in an old cluster. Blue straggler stars are one population that can form through mergers or interactions, appearing younger and hotter than surrounding stars of the same cluster. In extreme environments near galactic nuclei, repeated collisions could potentially build unusually massive objects. Stellar collisions are complicated because both stars contain flowing gas rather than rigid surfaces. Computer simulations show material being stripped, shocked, and mixed during the encounter. Most stars live without ever touching another sun. In the densest cosmic neighborhoods, however, crowding can eventually turn a near-impossible event into an important part of stellar evolution. Cosmic impacts may create exotic particles that survive for only moments. When matter collides at extreme energies, familiar particles can be transformed into short-lived states that do not normally exist around us. Cosmic rays striking Earth's atmosphere provide one natural example. Their collisions can generate showers containing muons and unstable hadrons before those particles decay into lighter products. Far more violent astrophysical environments may produce unusual combinations under conditions of immense temperature and density. Researchers study such possibilities using both particle physics and observations of high-energy cosmic events. Some hypothetical particles could help explain dark matter or other unresolved questions. Although no confirmed astrophysical collision has yet revealed an entirely new fundamental particle, the attraction of these environments is that nature reaches energies and scales unavailable in human laboratories. Neutron star mergers and energetic jets can force matter into regimes where established theories face severe tests. Any exotic state may exist for only a tiny fraction of a second before transforming. Yet its brief appearance could influence the radiation and particles that eventually reach telescopes. Cosmic catastrophes may therefore provide experiments that the universe performs for us. The universe's greatest catastrophes often become engines of cosmic creation. The most destructive events in astronomy repeatedly turn out to have creative consequences. Stellar explosions return chemically enriched material to space, allowing later planetary systems to contain elements that earlier generations lacked. Galactic encounters can compress gas and create immense populations of newborn stars. Neutron star collisions manufacture nuclei that ordinary stellar interiors struggle to produce. Even the activity around black holes can redistribute matter and influence which regions of a galaxy form stars next. None of this makes the destruction less extreme. Stars are erased, galaxies are distorted, and matter is thrown across enormous distances. Yet cosmic evolution depends on that continual recycling. A universe where matter remained permanently locked inside the first generations of stars would look very different from the one around us today. Much of the complexity visible now exists because earlier structures were broken apart and their material reused. Catastrophe and creation are therefore not opposites on cosmic scales. They are often consecutive stages of the same process. The universe builds new possibilities from the remains of events powerful enough to destroy what came before, and with that, we come to the end of our journey through some of the most extreme events in the universe. We have followed stars to the final moments of their lives and watched entire galaxies change under the pull of gravity. We have seen matter pushed into extraordinary states, while distant collisions sent signals traveling across space for billions of years. Some of these events last for only a fraction of a second. Others unfold over timescales so vast that no human lifetime could ever witness their beginning and end. And yet from here on Earth, we can still detect them. Their light reaches us across the darkness. Their radio signals arrive at our telescopes. Their gravitational waves move silently through the planet beneath us. For now, though, you can leave all of that far away. Let those distant galaxies continue their slow motion through space. Let the stars follow paths they have been traveling for millions of years. Nothing needs your attention now. Allow your breathing to become easy. Let your shoulders rest a little more heavily. Feel the surface beneath you supporting your weight and allow the last thoughts of the day to become less important. If you enjoyed this journey, like the video, subscribe, or leave a thought below. It helps more curious minds find their way here. And if you are somehow still awake, there is another video waiting for you on the screen. You can follow it into another part of science and let the next journey carry you a little further towards sleep. But if you are already beginning to drift, there is nowhere else you need to go. Just rest now. Sleep well, and good night.